Hello, all of you. Now let's take up one discussion called as GCM model. Essentially, we are looking at the atmospheric circulation models. Your syllabus talks about the Ferrell's model. We do know about Hadley's model. We know about the modifications on Hadley to give Ferrell. But you can also know something about what's called as the GCM model, which is the global computer model that talks about the atmospheric circulations. Now see, you can give a heading, GCM model. Ferrell's model and Hadley's model are not really based on mathematical calculations. They are not based on statistical analysis. It's a kind of an imagination that they had. They kind of figured out what must have been happening. So it's not really plotting of exact wind pattern, plotting of exact pressure patterns. So it is very crude approximation of what must be happening. Whereas the GCM model is a mathematical model. It's almost like a mathematical simulation using statistics, data. They have wind data, temperature data, pressure data. They put all of that into a program, and the program then depicts what the circulation looks like and how the circulations can be in the future. So GCM model in that sense is a more realistic and is a more real-time modeling. I repeat, if I'm missing, I repeat this point here, that if you look at the type of atmospheric wind circulation models we have, Hadley-Haley model and the Ferrell's model are more like approximations. They are more like imagination what the circulation systems can be. So it is very intuitive in terms of what they thought was happening, not really based on mathematical calculations. Whereas GCM model is a mathematical model. It is a statistical model. It uses a lot of data. These are computer-based models. You feed the data, and the data then is processed to tell us what the atmosphere probably is looking like. So that way, I repeat, GCM model is a realistic model, and it is also used for weather prediction. In fact, most of the weather forecasting models use some modifications or refinement of the GCM model. And this also applies to the monsoon winds. Monsoon prediction model also based on a dynamic system of computer modeling. So please look up page number 99. We have the wave theory, we have the tricellular model, and we have the GCM model. I think you all know about the wave model. To the tricellular model, if you add the Rossby waves, to the tricellular model, if you add upper tropospheric wind systems, it then becomes the wave model. Whereas the GCM model, I'm reading out from the book now, page number 99, global computer models are basically tools for weather forecasting on the basis of simulation of real weather phenomena, and involves laws of physics and mathematical principles such as laws of motion, principles of thermodynamics, basic equations related to atmospheric motions, and airflow and hydrostatic equation. In fact, the GCM are set on computer-generated maps of weather conditions of real atmosphere, and these maps are used to predict the future weather conditions. So it's a very realistic model for prediction of the future weather conditions. What I'll suggest is, see, GCM model, I don't think they'll ask you. But if they ask you a question about upper tropospheric winds, if they ask you a question about circulation models, this can be a nice conclusion maybe, that given the complexities, given the numerous factors involved in the circulation process, more reliable models are those that are based on computer simulation. Models which are based on real-time data analysis, models which are based on actual mathematical and physics analysis, okay, that depict and that predict the patterns. They are more reliable than models like Hadley's model, Ferrell's model, wave model, and so on. Let's move on, please. Now that you have asked me wave model, okay, can you open up page 99? Because you've asked me wave model, open up page 99. Okay, so I'm just reading our first few lines here. It says, the wave model is based on the concept of transfer of heat energy and angular momentum. It may be mentioned that this model retains the basic structure of tricellular model, but views the roles and relative importance of the three convective cells differently. Okay, it says, this model emphasizes horizontal transfer of energy and angular momentum rather than meridional transfer in the vertical plane. Guys, if you remember, we had asked you a question, write a note on the mechanisms of energy transfer, okay, something around the net radiation and so on. So listen, all of you. If this is the Earth's surface, and if this is the tropopause, that's the equator. The conventional model said that air rises up, air shifts, air sinks, air again goes towards subpolar and rises. And it is this type of vertical circulations which are responsible for energy transfer. Okay, the tropical areas are warmer, okay, and they transfer heat towards temperate regions. From the temperate regions, the energy transfer towards the polar regions. So the conventional model said that the energy transfer across latitudes happens by the vertical meridional cells. But the wave model says, no, that is not the most important mechanism. The more important mechanism in energy transfer is the role of the meandering waves. These Rossby waves that we have, I hope you all know these waves. These Rossby waves, they are more important in exchanging the energy across the latitudes. The Rossby waves, they take energy from the tropical areas, subtropical areas, take it towards the temperate regions. They again come towards subtropical areas, again take it towards temperate regions. A lot of exchange happens because these are areas of high and low pressure. If you remember, we talked about those temperate cyclones. So temperate cyclones, frontal activity, and this type of north-south meandering waves, these are responsible for energy transfer rather than the vertical circulation cells. Now this is what? Page number 99. I am repeating the sentence here. Page 99, first column, I am reading up the 12th, 13th line. It says, this model emphasizes horizontal transfer of energy. Here, horizontal means, okay, it is in the across the latitudes, not in terms of the vertical circulation cells. Emphasizes the horizontal transfer of energy and the angular momentum rather than meridional transfer in the vertical plane. Thus, the wave theory model is based on the mechanism of conservation of angular momentum and the poleward transfer of energy and momentum to maintain the planetary wind systems. I hope you've understood this. So to the tricellular model, if you add the idea called angular momentum conservation, then you get, okay, the wave model. So I'm done with the circulation models, the GCM models that we can talk about. Page number 104, 105, just to tell you what you should also cover. Page 104, 105. Say if you have a question that says, discuss the components of mid-latitude circulation. Please write the question. Discuss the components of mid-latitude circulation. Essentially, what we're asking you is, tell us what are the winds, what are the systems of atmospheric circulations of the mid latitudes. So in the mid latitudes, you will again talk about surface winds and aloft winds. And you'll also talk about the smaller regional scale circulations like temperate cyclones. So if I want to summarize the answer of what are the components of mid-latitude circulations, talk about westerlies first, then you talk about upper tropospheric winds, you talk about the Rossby waves, and you also talk about the polar jet stream. I repeat, you talk about the westerly winds, that's the surface global wind. You'll talk about the upper tropospheric winds, okay, because upper tropospheric winds become more prominent as I move towards the poles. With the upper tropospheric winds, move on towards Rossby waves, the meandering Rossby waves. And with the Rossby waves, you'll then talk about the jet streams also. The polar front jet stream. You can also have a mention of subtropical jet stream, although it's more towards the tropics. And you also will add temperate cyclones. Temperate cyclones are also very important component of mid-latitude circulations. You'll add temperate cyclones. You'll also add air masses, because air masses are perhaps the most important aspect that controls not just the temperate weather conditions, they also control the weather conditions of the tropical, subtropical regions. So when you add all of this together, then you get the components of mid-latitude circulations. So come to the textbook now, page number 104. Let's move on now. Remember, I asked you a question. Yeah, listen. I asked you a question. What is the impact of shifting pressure belts? Now, shifting pressure belts, I'm sure all of you would mention the monsoons and also the Mediterranean type of climate. So that was not the very big issue. The challenge was something else. Look at the screen here. Say this is your answer page. Okay. And the question was shifting pressure belts. You could start the answer by saying that global pressure patterns are in the form of zonal belts and cells. And these cells or belts, there are seasonal modifications and there are seasonal changes. You can have a small diagram if you want, telling us some of the names of the pressure belts. So subpolar high, the subpolar low, subtropical high, the continuous belts. You could have some jottings here. So in about 1/3 of page, you could have depicted what is the pressure pattern. Now you come towards what does the shift do? See, in your body, I had said, you have to bring in geography here. Geography in the form of bringing concepts of geography. And another very important way of discussing geography is regional comparison. Okay, so see, couple of tools you'll have to remember in your answers. Regional comparison, as in maybe the impact of shifting pressure belts in the equatorial regions is different from the shifting pressure belts in the tropical regions, is different from the impact in the temperate regions. So if you can compare like this, then I have a regional pattern. Like for example, we all know this, that the pressure belts do not shift as dramatically in the low latitudes. the shift is more dramatic in the mid and the high latitudes. The shifting pressure belts, they are more pronounced with seasonal changes, and the temperate cyclones of the mid latitudes. So that's one. Okay, what's the impact? You discuss the impact on the mid latitudes and discuss this with the temperate cyclones. Second impact of pressure belts, you can talk about the impact on the Mediterranean type of climate. So that's the easy one. You can draw a small sketch and show that. The third impact is the impact in the tropical areas. And you can have a mention here that tropical areas, in general, the shift is not much, but the impact of the shift is more pronounced on the land. Okay. So if you remember India's map, the ITCZ shifts right up to 20 latitudes, sometimes as much as also 25 latitudes. And because of this shift, the southwest monsoon winds are attracted and they end up covering the entire India. If the pressure belts, if the ITCZ has not shifted as far as this, perhaps India would not have monsoons. So what I'm telling you is, rather than just mentioning that monsoons are a consequence of shifting pressure belts, we make the discussion a bit more inclusive of geographical concept like land-water differential. And then you say that the monsoons are a consequence of this type of a shift. The fourth point you can add to your discussion is that I said equatorial regions, they do not have much impact of shifting pressure belts. Why? Because there is not much of insolational variation, and hence the shifts are not pronounced for the equatorial regions. But then again, you can add that on the land, there is some more shift than on the water. So if you remember Africa here, equator here. In the summer, the ITCZ does go a bit northward, because of which we have the pseudo monsoons of the Gulf of Guinea coast. Okay, so it is monsoons, not like India, but it is still monsoons, but it's feeble, impacting that equatorial regions, and this is generally within 10 or 15 degree latitudes, unlike India, which is up to 25 degree latitudes here. So it's a passing reference that equatorial regions do not have much shift, but then Gulf of Guinea does show that the pressure belts can shift a bit more on the land. The fifth component you can add is, how does the pressure shift impact the upper tropospheric winds? I do not know how many of you were able to do this. Some of you would have missed this entirely, okay, but others would know that the shifting pressure belts does impact the north and south position of the STWJ. If the pressure belts would not have shifted, the subtropical jet stream would not have shifted, and without the shift, we would not have the western disturbances. We would not have some of the components of the monsoons. Apart from this, okay, the shifting pressure belts of the high mid latitudes are associated with the Rossby waves, okay, and you can go on talking about the cyclones there. So what I expected was, you should have combined the shifting pressure belts with the regional pattern, and maybe you could have added a 6th point, that the shifting pressure belt is not such a prominent phenomena in the southern oceans. We have subtropical, okay, subpolar low pressure. It's all water, fairly equalized temperature. So in the southern hemisphere, you not have as much impact of the shifting pressure belts. So a regional pattern based discussion on how the shifting pressure belts can impact. Okay, fine. So you have an idea about how you could have managed this question. And page number 109, page 109, there is some write-up on this shifting pressure belts. It's just that it is not discussed in as much detail that we would like it to be discussed. I think some of you missed out. Look at the screen again, please. So shifting pressure belts, okay. We have discussed it on the basis of different latitudes. Okay. We talk about the shifting pressure belts in the temperate regions, in the Mediterranean type of climate, in the tropical type of climate, monsoons, equatorial regions, and the upper tropospheric winds. 5 is upper tropospheric winds, including the impact on the jet stream. Now listen, see what happens. The pressure belts of the mid latitudes, this is North America, this is Eurasia. Where do we have the subpolar low pressure? Somewhere here. Where do we have the Siberian high pressure? Somewhere here. So what happens is, when the pressure belts are shifting north and south, these cells also start shifting north and south. In the winters, this becomes prominent and well contrasted with the subpolar low pressure. In the winters, okay, the Siberian high pressure, it exists, and this is strongly contrasted with subpolar low pressure. And this interaction creates air masses. What happens in summers? In summers, the subpolar low pressure weakens and kind of moves a bit northward, okay, whereas the Siberian one doesn't exist really strongly. So in the summers, the subpolar low pressure, because of its weakening and because of its northward shift, it is not contrasted with the continental high pressures. In any case, the continental high pressures have weakened in many places. They also have disappeared. Is it okay now, all of you? Essentially, if I do not have this contrast, then I will not have, okay, prominent temperate cyclones. Okay. In the summers, this has gone northwards. We do not have air masses contrast between tropical and the temperate ones. But in the summers, in the winters, we have a good, well-developed on the water. This has now come down. This well contrasted with Siberian high pressure. The system now sets up for temperate cyclones. Okay. So we basically had to mention that the shifting pressure belts and the land-water differential together are responsible for, write down, shifting pressure belts and land-water differential is responsible for development of air masses in the winters and the temperate cyclones. Now, for referring this, you can look up page 110, 110. 110. Okay. First column, last paragraph. The regions lying between 60-70 degree latitudes are characterized by two types of winds in a year because of shifting pressure and wind belts. With the northward migration of sun, at the summer solstice, the polar easterlies are weakened during northern summer, okay, and extend over subpolar. It's quite opposite southern hemisphere. Then it says that this situation is reversed at the time of winter solstice, when there is southward migration of the sun. The polar easterlies are well established, okay, and this results in the typical climate characterized by, okay, wet summers throughout westerlies and cyclones winters in the polar easterlies. So this discussion is based on what's happening in the polar regions. The same you also apply for the temperate region. Page 110, 110, first column, last paragraph.